All right. Hello, everyone. I'm Dennis Soemers. It's great to see you all here at ACG. And I'm happy I get to introduce Professor Mark Winands as your keynote speaker today. Mark is currently a professor in machine reasoning at Maastricht University's Department of Advanced Computing Sciences, where he's also been serving as department chair since 2021. His early research, this is going back to the early 2000s, it revolved around intelligent search for this game called Lines of Action. He worked on evaluation functions, on variants of proof number search, forward pruning methods, among other techniques. This led to his PhD thesis, which he defended at Maastricht in 2004. This was supervised by Professor Jaap van den Herik, who we also see here today. It also led to recognition. It received the ICGA Best Publication Award for 2004. And his Lines of Action program claimed many victories at computer Olympiads, I think up to and including 2015 at least. After this, in 2006, Mark also worked as a postdoctoral researcher in Reykjavik University. I think you were actually the very first postdoctoral research ever across all of Reykjavik University. That's a fun fact. And I think you were not the last postdoc at Reykjavik, so I think they were happy with the experience. After this, Mark returned to Maastricht University, where he still is today. He supervised many PhD students we know well in the community, including Guillaume Chaslot, Maarten Schott, Jan Takashi Saito, Pim Nijssen, Hendrik Bayer, Chiara Sironi, Tom Papels, maybe myself as well. I met him back in 2011, 2012 as a bachelor student, and since then he has not been able to get rid of me. He's also continued to provide extensive service to our community, serving as, for instance, editor-in-chief for the ICGA journal, associate editor for Transactions and Games, organizing conferences, such as previous editions of this one, Computers and Games. It was still called CIG, I think, in 2018. He's also actively been involved in Monte-Carlo research ever since the beginning, really 2006, 2008. And that's what we will hear about more today, but not about his past research on MCTS from the early days, but we will hear about new adventures with Monte-Carlo research. It's my pleasure to give the floor to Professor Mark Winands.
Okay, thank you, Dennis, also for introducing me, and it was also a pleasure to see you again. Also, I would also like to thank the ICGA organization for inviting me for this online talk. As Dennis already indicated, I'm also currently at Maastricht University, and I'm actually in this building. So if we will have the event next year, we will also have this in this building, so you already know where you have to be also for next year. To give a little bit an outline of my talk, as already Dennis indicated, I will mainly talk about the future of all the new things I'm doing with MCTS, but I will also discuss a little bit of background, and because otherwise I'm afraid that some of you will miss some of the points I would like to make. So there will still be a little bit of history. And I have called this talk New Adventures in Monte-Carlo Research. Well, I had to come up with a title, and I thought that adventures was actually a very nice phrasing for this. So I will focus, amongst all of the stuff that we have been working at Maastricht University, of using MCTS for real-world applications, looking how we can use MCTS in a more generic way as a stepping stone for artificial general intelligence. We also have exploring of using MCTS for quantum computing, and last but not least, nowadays we're talking about explainable AI, and here I would also discuss a little bit about explaining MCTS results. Now, to kick off, I always have been interested in building machines or building engines that can beat the best humans in games. So really, I always have focused on game playing myself. And this has always one of the first tasks of AI. And most of you have seen that we have accomplished a lot over the years. And the main AI mechanism to do this always has been search. And everybody knows the classic framework of the so-called Minimax algorithm, that you simply start from your initial position, you start looking at all the options, and then you will look to all the options for the opponents until you reach a particular search depth, because you don't have the time to search everything until the end. And then at that moment, what you always do, if you have also paid attention at your AI class, people have been using so-called evaluators to assess the state that we have seen till that far. That can be by a so-called classic evaluation function. Nowadays, people are also generating them by using ChatGPT and all kinds of other tools, or a so-called neural network. And if you then apply the Minimax principles, you will find the optimal line of play, assuming that your evaluation function is also doing a great job. Now, the issue here was, this was the model I was taught back in the 90s when Jaap van Heerijk was still my professor. But even then, we already had some issues with that. Well, this works very well in a certain set of games, and especially in the 90s, we saw that Deep Blue defeated Kasparov in chess using this Minimax alpha beta search framework. We have seen our former president, Jonathan Schaefer, exploring how to use alpha beta Minimax in the game of checkers. And here you see myself as a PhD student doing some research in lines of action and also playing against the best player at that moment. And we also have done this in other games. Now, the issue was at the end of the 90s, the early 2000s, that this mechanism not always worked very well. And the classic example always have been Go, where building a classic evaluation function turned out to be a very hard thing. And when I was a student, Jaap took me all the way to London to play or use my engine in the Lines of Action tournament. And at that moment, they were also playing the Computer Go tournament, and people were laughing about the quality of the games, because what turned out to be with this classic model of Minimax, what are you going to do if you lack the knowledge to build a heuristic evaluation function? Because you need one to assess the leaf nodes. What are you going to do if you don't have the data to generate one automatically? For instance, by using a neural network. Or what are you going to do if you don't have the time to generate or build one? Or after all your efforts, the evaluation function still does not work. Now, after my PhD research, a new mechanism actually popped around, and I think the first one that actually reintroduced it in the gaming community was Buzy, was the use of so-called Monte-Carlo evaluation. So instead of using a board evaluator that looked at a couple of features and would weigh them, you would simply play a number of random games and using the scores of them in order to calculate a statistic. For instance, you would play 10 games, and if the first player won 8 out of 10, you would simply score this as 80%, or in this case, only 75%. And with such a mechanism, you could basically assess all the leaf nodes, and then you would backpropagate this in the Minimax fashion, and then you would find a principal variation. Yeah, this mechanism had only one problem, is that the quality of the gameplay was still so-so. One of the jokes was, if you are using Monte-Carlo evaluations, you're averaging, and then your final tournament result was also average, because usually these bots ended up in the middle of the pack. One of the main reasons was because these Monte-Carlo evaluations are actually pretty time heavy, which means that you can't look that deep anymore. And then especially you would have problems as I indicate here. Sometimes you really have a narrow path to win. And then with Monte-Carlo evaluations, you either could underestimate or overestimate your position. Because as we see in this case, you have one move that is actually leading to a winning position, whereas all the other ones are really bad. Now, in this case, if you would actually random sample, you would simply think you only would win 33%. But if you would have looked a little bit further ahead, you would have seen that you won all the games if you played the right move. And then, of course, your principal variation would change as well. So the whole issue with this Monte-Carlo evaluation is that you also assume that the samples must predict actually quite reliable. It has to have a correlation with the game theoretical value, and especially in a game where you have a lot of traps or there's narrow path to the winning, this can become problematic. As the node evaluation is pretty slow and you actually don't look ahead that further anymore. Now, the solution came around at the Computer Olympiad of 2006. I was actually co-organizing this at that moment. And then Rémi Coulon came around with his 9x9 Go engine using a new mechanism he called MCTS, and he won the tournament. Now, the whole idea of MCTS is that you don't start with already search tree and start assessing the leaf nodes. No, you actually flip it. You start actually with the sampling first, and then you build up a tree gradually. Which means you play a game, you add the first position that you haven't seen so far, you add it to the tree. And then whenever you come across a node again, you will expand this node a little bit more. And you backpropagate the results. So at a certain moment, you get a pretty good idea what the results were if you would play in a particular direction. So you keep track how many times you won and how many times you played this particular node. And then at a certain moment, you got a certain mechanism that every time in the route, you would select the most promising node so far. And you would also do this for the opponent based on the statistics. And then if you entered a node or state that you haven't seen before, you add it to the tree, and then you simply play it out, which means simply you play a simulated game until the end, and you simply score it, and you backpropagate these results again, and you update the statistics. Now, this looks all very nice. The problem is, of course, you would also still have to balance this. Because if you would now use this example and you would play in a very greedy fashion, then you would always go for the first move and you would never look anymore at the second and the third one because you didn't score that well anymore. Now, to balance this, one of my former colleagues, Levante Kotschitz, came with an idea called the so-called upper confidence bound applied to trees algorithm, which has been based on the multi-armed betting problem, where you simply assume you go to a casino, you have a lot of slot machines, and you would like to figure out the slot machines which is giving you the highest payoff. And UCB is a mechanism to handle this, and what Kotschitz and Svetfari actually proposed is to use this in an MCTS framework, so actually in the tree. So you get track of the score so far, which I call here VI, plus you keep also track of how many times you actually played the move or how many times you pulled that arm. Now, by using this magical formula, you could balance exploitation with exploitation. So exploitation indicates that you should go for the more interesting positions, and exploration still says, well, you should still try also the ones that didn't look so far, because a slot machine or a move that doesn't look promising, if you would try this out a little bit more, it could be actually that this is actually more fruitful than you actually thought. Now, what we did at Masters University, and then I would like to go a little bit to the past, because some of these ideas I will later explain. We try to improve this whole MCTS mechanism, and I have selected 7 add-ons that were successful over the years. And the first one was so-called progressive bias, also progressive history if you didn't use any knowledge. And here the idea was that to use some knowledge or knowledge that you gathered during the search in order to bias the UCB mechanism. Because UCT needs some samples in order to say something meaningful. However, if you enter a node where you haven't sampled a lot, it actually still plays quite weak, and then actually using a bias could actually improve the play. Another problem that we tackled was that UCT would work actually pretty well, was that you assumed also certain branching factor, which was actually feasible for 9x9. But if you would go for, I say, with somewhat gains with a higher branching factor, this wouldn't work out. And therefore, we introduced the idea of progressive widening, that you say, well, let's only focus on the 5 or best 10 moves first. And at the moment, I visit this position more and more and more. It's probably a very interesting line, and then simply start looking at more moves, because you should never do aggressive pruning on your main line. So over time, in that particular position, you would look at more and more states if you would visit it more, because it is actually more promising. This was also done with my PhD student, Guillaume Chassot, as Dennis already indicated. Now, also that we had a look at was actually how to parallelize MCTS. It turned out that parallelizing MCTS was actually quite fruitful, because MCTS assumes that you are sampling, and if you're sampling, you also make mistakes. Now, in parallelization, usually the issue is you have these racing conditions, but as MCTS already can handle to a certain extent, and is pretty robust of making mistakes, you don't have to worry about these racing conditions. So it's relatively easy to parallelize MCTS, and that's something that we explored also in our research. Now, another one that we had a look at was at the so-called play outs, when you actually are randomly playing a game. Now, it turns out that if you weight the moves based on some knowledge, it actually starts to perform better, because you get actually more reliable statistics. Now, the issue is that you don't always have knowledge, and therefore we came up with the idea of using n-grams, that you looked at a certain action sequence and how successful a particular action sequence was, and using then some roulette wheel selection then in the play out to select the more promising action sequences more often than the lesser promising ones, also then actually giving you a more reliable statistic without actually implementing domain knowledge. Now, also what we explored was a little bit the fact that you don't have to play always that simulation till the bloody end. You can also dynamically cut it off at a certain moment, and it turns out to be that actually this improves also your play. And one of the last one, and I'm always done, is also we looked also how we could then, if you play the next move in the game, whether this is in a board game or in a video game, to reuse certain information of the tree. And we also did quite some exploration about this way of reusing information. Especially also Dennis did this for his video game AI engine that he developed for the general video game playing competition that was also MCTS based. Now, in the end, you will get a lot of parameters which you have to set beforehand. And as you not always know what your opponent is going to be, or in which states you will actually be, we also came up with the idea of self-adaptive MCTS, where we use ideas from evolutionary algorithms and tuple bandits in order to tune the parameters also online during gameplay. Now, as you all know, this whole MCTS mechanism was also used in AlphaGo, DeepMind, and in the end, with that combination of MCTS and neural networks, the best Go player was also defeated. And this idea was also later used in shogi and chess. And to make it always very clear, a lot of the performance gain was actually based on the use of MCTS. If you would look at that paper again, then they also admit that the raw neural network would only play at 3000 ELO points, and adding the MCTS on top of that would bring it to 5000 ELO points, which means you don't have any chance to win anymore. Now, what we did in Maastricht, we never entered this computer Go race anymore because we already saw that we would not win this anymore, and we moved actually looking at how to use MCS for all kinds of other games. So, for instance, some of my PhD students have worked off using MCS for single-player domains, especially puzzles. Other ones have looked at games with multiple players, and I'm talking about 3, 4, or 5 players, where you usually have the issue also with the kingmaker, because you don't have equilibrium points or one equilibrium point as a 2-player game. You can have multiple ones, which is always very tricky. Turns out to be that MCS actually works in quite of these games actually quite well. Of course, most multiplayer games do also have an element of chance or imperfect information, and we also have been using successfully MCS for games with chance or imperfect information, just like Scotland Yard. And one of our last ones that we actually looked for as a single game was the use of MCS for video gaming, because there the big challenge is that the state is changing all the time. You don't have that much time to think, which means that you have to also to use some parts of the MCTS from previous considerations in order to make still a good decision. And here we have been very successful in some of these video gaming competitions, as you see here with Pac-Man, but that also my PhD student Tom Papels did. Now, if you will come next year to Maastricht, I still have a bunch of PhD theses lying in the closet, and you can also pick them up if you are still interested here. Now, as Dennis already said, Mark, you shouldn't talk too much about the old stuff, also go a little bit to the new stuff. And one of the things that I was always interested in, okay, we do all this game playing, and what we always tell our colleagues or our funding agency, that we could also use these ideas also for real life applications, because that's basically what we always are promising, because otherwise we can't get funding anymore. Especially this approach has actually been very successful for planning in games, and especially in applications that involve sequential decision making. And there are many real-life situations where this is also the case. And my question has been for already a decade, can we use our game AI search techniques such as MCS also for all kinds of real-life applications? And I've worked on a couple of domains, and I will show you 2 of them. And one of them was with a German company called AUKUS. And AUKUS is developing huge production lines for plating all kind of tools or items. Could be like you have a kitchen cabinet, and you would also like to plate your baskets, because you would like to have a very nice chrome layer or some plastic layer around that. And that is a quite complex process, which means that that particular item has to pass several machines on a production line. And what these manufacturers actually want is that you can do as many different jobs as possible. So at such a production line, there are all kinds of machines where that not every job should use. And then what happens is that usually during a day, they have several items that have to be processed, which don't need to use all of the machines on a particular production line. Moreover, you have many of these lines also in parallel, and you could also switch your item to another line as well. Now, another complication that they also had was you can make a plan, but there is then actually a scheduler, which is actually a black box that decides how the schedule will look like, because there are also some safety checks that still have to be made, and that is not given. So this is actually a case of black box job scheduling with a lot of possibilities as well. You have to think that you easily can have 6,000 jobs, and you have to distribute them over 3 lines with 100 or 150 machines. Now, what they were interested in was to sell also a little bit of AI when also selling the production line, because when the production line is built, you can't change it anymore. So you would like to have some nice software who could actually schedule all these jobs nicely. Now, what did we do was, frankly speaking, to use MCS and using all kind of ideas we took from our research. So as this is a single player version, because there's no opponent, we looked how we did this for puzzle games. As we had really no idea what are the great actions, we use domain independent techniques like progressive history to bias the UCB and n-grams to bias the playouts or the rollout. We use tree reuse, parallelization, and we also use neural networks to predict the behavior of the black box. Now, when looking at one of their big industry case studies, they had also at every day could happen that they would have to process 6,000 jobs of 16 types across 110 machines, having also 3 different lines. And then the whole idea was to improve the lateness and the make span, because they would like to reduce the amount of time that machines are idle, which means you could either then increase the production or you could stop the production actually earlier, which would also save your time. And based on that, in 1 minute, we were able to get better plans than they currently had, and basically reducing the make span with another 10%. So this is now actually being deployed in their production lines. And you see here how MCTS and game research can also be used in real life. And another one we have been looking at is also how to use MCTS for structural engineering. And here it was more about if you build these big apartment buildings, especially in regions where there are also earthquakes, like in Italy, you would also be very sure that the load-bearing elements are placed also correctly. Now, people know how to do this, but if you would change your design, then you would like to figure out how to and where to put it quite easily. So basically, we represented or we built a model or discrete a model where to place these elements and to see if we can come up with better designs than the current state of the art. And here we tested MCTS on 4 different types, consisting each of them with 200 similar design tasks. And there we designed a genetic algorithm using MCTS. So basically what happened was that MCTS would do already the initial configuration, and then the genetic algorithm would then actually refine it. And this combination worked better than the other approaches proposed. Now, this is all fun, but you could start asking yourself the question, if with MCTS you can play games and you can solve real world problems, can it also become part of so-called AGI, artificial general intelligence, systems that can perceive, act, communicate, learn, and also plan and make decisions? Could MCTS actually help for that latter part? And this is something that we have been working also for a while. And if you look a little bit at the history, around 2005, this whole general game playing vibe came around, where the idea here was to build engines that could play any game at any time, or video games at any time. And then you see that MCTS with some online and offline learning actually worked out very well. Even in video games and these arcade games, and also Dennis can tell you a lot of stories how we have used MCTS and some online learning in order to become also one of the best agents here. Now, what we actually learned here is that MCTS actually worked out pretty well for many games, but there always then, if you come up building such a bot, is that always a couple of games where it doesn't work very well. So there is no free lunch here. So there is no single best search algorithm or best MCTS configuration that performs in every game very well. This really depends on the game. Now, in the past, all kind of solutions have been proposed, like using algorithms that could tune online some of the control parameters of MCTS. So when you're playing a game X, then you would simply increase the UCT constant or decrease it, or you would change the randomness, etc. Or for instance, to use a portfolio of different engines and then let them actually play or search in parallel, and then use a kind of voting mechanism, and then go for the action that was actually selected the most of all these different search algorithms, and so on. But this is still actually dependent on some human decisions, because the human will still decide which parameters that can be tuned online. What would be the range of actually tuning these parameters, or the values that you could actually tune, which search algorithms you put in the portfolio. And most of the time we also have been cheating a little bit, because if you look to all the successful MCTS applications, they also were combining some other IDs from other search algorithms. So what we also have been doing here is also building all kind of MCTS hybrids. So MCTS that is using IDs from Minimax, just like MCTS solver using or labeling proofed nodes, and then actually backpropagating them using alpha beta search in the playout in order to improve the simulations, using some domain knowledge that was also being backpropagated together with the statistics, and then you would actually get a hybrid of Minimax backups and all kind of other variants. Some of us also look to other IDs. So for instance, Dennis combined MCTS plus iterated with, and then using novelty pruning in his engine. And one of the last addition here is also combining MCTS with proof number search. Now, and that is the one I would explore a little bit further, so you also get an idea of the message I would like to give you. So recently we came up with the idea of PN MCTS, which stands for proof number search MCTS. And the whole idea is, assume you already have your nice MCTS tree. You did a couple of samples and you see I've already have given the node certain statistics. So node B I played 9 times and won there like 38% of the times, etc, etc, etc. And what you simply can do is simply, because you already have such a tree already in memory, you could also give the nodes also their proof number and disproof number score. Now, what would this be about? Basically, every time that the second player is to move, you will treat this at a so-called AND node, whereas the first player you treat it as an OR node. And then basically at all of the leaf nodes, you will assign a so-called proof number and disproof number. Whereas if the node hasn't been solved, you set the proof and disproof number to 1. If the node has been solved in the sense that it is a win for the first player, you set the proof number to 0 and the disproof number to infinity. And when it is a draw or a loss, you put the proof number at infinity and the disproof number to 0. Now, and then you actually can use the theory of proof number search in order to update the proof number and disproof number of also the internal nodes as well. Which means that if you are at a so-called OR node, you always take the proof number of that was the smallest of all the children, and the disproof number is then the sum of the disproof number of all the children, and for an AND node it's all the way around. And that's something you can get actually basically for free, because you're building a best first search tree anyways. Now, what you can then basically do is to use the proof number or the disproof number to bias the UCT mechanism. Now the problem is you would have to mix proof numbers and disproof numbers with statistics. That doesn't work out very well. And here our idea was simply to look at the rank, which means that all nodes are ranked based on their increasing proof number, in case you are at an OR node, or you order all the children of an AND node based on their disproof number. And you do this in increasing order, which means that the one that has the lowest proof number will get the value of 1, and you would go all the way up, and you would use this rank in order to bias that particular UCT node. Now, one of our collaborators, Jakob Kowalski and his team, he also verified our results, and he also tested this in a couple of games to see what would be the improvement. Now, in Lines of Action, my favorite game, it was around 90% when adding this mechanism to it. In other games, it was around 2/3. But you also see, and that is also the story I would like to make here, you always have a game where it doesn't work out that well. Now, and here it basically comes, and it has been something that I always have been wondering about. Shouldn't we adapt the search automatically to each new unknown problem? Yeah. Should we actually come up with a mechanism that is able to start configuring or combining some ideas from other search algorithms in order to make a better one? Because at this moment, we do this as human developers. And it's basically a mechanical process. We simply add some components, we change some of the components, we add some components from a different search algorithm, and then we design a new one. And sometimes these hybrids work very well, and sometimes they don't. But can't we automate this? Why should we ever do this? Why should we always do this all by ourselves? Now, what I proposed already a couple of years ago, that we should go to a so-called adaptive general search framework. And here the idea was you would have a portfolio of search algorithms. You would also collect the performance of these search algorithms. And based on the domain, you would select a certain set of them, and you would start also trying them out. And based on that, you would also start generating new ones by actually testing them out. Now, the question is, of course, how are you going to do this? Now, as of this year, I started the so-called project FrankenSearch, where I try to design search algorithms completely automatically. That sounds to be a very crazy idea, but just like Frankenstein took elements or parts of bodies from other people and designed something, here the idea is we take parts of other search algorithms and we try to design them automatically. Of course, there are a couple of questions that have to be resolved first. And one of the main ones is, okay, how should we then also represent our algorithms in such a way that we can start actually combining ideas from other algorithms? And here the idea would be simply to start thinking about what are the most atomic features or the most atomic elements of a search algorithm. And if we can define this, and then at a certain moment, we can also come up with a mechanism to select these parts and also to generate them in such a way that we get something new. Now, what we did now in FrankenSearch, and we will submit the paper soon to the ICG journal, we came up with a new language, which we called SADL, which stands for Search Algorithmic Description Language. If you look very closely, you see that it also looks a little bit like the Ludi language for actually also developing or describing games. But we took the same mechanism for search algorithms, which means we would actually look at what are the most element parts of a search algorithm that you always see, and then start defining their atomic elements here. So for instance, for MCS, we have action selection, we call this UCT. There are conditions when we apply this in the tree. Now the selection mechanism using a maximizer function, and then it uses a function like UCB. And you also can generate also different value functions. Now, what we already have done, we have developed this algorithm and we have implemented a couple of these search algorithms in our language. And we have been using evolutionary algorithms to see if we can come up with new variants or new combinations. Of course, the tricky part here is that the number of possibilities that you have actually explodes. So no great results so far, but as a proof of concept, and I would also like to invite everybody when we publish this paper to start also working on the project FrankenSearch in order to come up with a system that can actually make new search algorithms. Now, This was our second adventure. My third adventure also starts for my earlier research of also looking at how to make use of modern hardware, especially around 2005, 2006. We saw also more and more that machines had multiple cores, and then the whole idea was also how could we use or how could we parallelize MCTS. Turns out that MCTS actually scales very well. The question is, of course, we will also be at a certain moment also in the quantum computing area, and can also MCTS play a role there? Now, the first or the next adventure I would like to stress here is also how can we use MCTS in supporting quantum computing. And here, what we looked at is at so-called optimizing quantum circuits, which means you encode your problem in a so-called parameterized quantum circuit that you see here with AND, OR, and NOT gates. Of course, these are quantum gates, of course. Also, these quantum gates, they also have all kinds of parameters you could set. And then the whole idea of quantum architecture search is finding a topology, including the parameters, to come up with a circuit that actually could solve or would give you an outcome for a particular problem. Now, the issue is how would that circuit look like? Now, the assumption is that if we have a quantum computer and we actually could code such a circuit, we could solve this problem actually instantly. Now, here, the MCTS is then actually being used to actually build or actually design the quantum circuit. Again, it assumes that you have also a quantum machine, and luckily we are using here so-called quantum simulators that emulate the behavior of such a quantum computer. Now, the MCTS then start actually adding circuits. It can also, it can start adding gates, can also swap gates, can also remove gates, can also set the parameters of a gate. And every time it is checking in how far what the outcome for that particular problem would be when using that circuit. Now, such MCTS-based quantum circuit design has all kinds of applications. For instance, estimating the ground state energy of all kinds of molecules, for solving systems of linear equations, for particle track reconstruction, for handling max-cut problems, for solving Sudokus, and also for handling quantum random circuits. Of course, I still have to give everybody the warning here that there is no guaranteed quantum speed-up here. It could be speed-up, but not a quantum speed-up. Now, what we have done is also looking at improving the current state of the art, where people were already using MCTS. And what you were seeing is that, of course, for all these problems, the branching factors can actually explode. And then in a lot of these articles, they were using all kind of heuristics and all kind of ideas to reduce that branching factor. Whereas we said, okay, we could do a better job here. So what we proposed was also still to use MCTS, but then also using progressive widening, an idea that we tested already ages ago in 19x90 Go, where you also had to use branching factors, where you basically could, without any domain knowledge, could handle domains with huge branching factors. Now our approach led to smaller circuit depths, also then using less gates, but still giving the same solution quality or even better, and also using less classic and computational resources in order to solve the problem. And that's not something we only tested on ground state energy of water molecules. We also compared this with other ground states or even systems of equations. And every time it turned out in our tests that we were faster at less complicated circuits, and the performance was the same or even better. So again, you see that ideas coming from the game of Go can be used also for designing your quantum circuits. Please also put this in your grant application when you're doing MCTS research. Now, the big question starts to pop up if you start doing this, is what is not happening, especially when using MCTS. Because Of course, MCTS is not like a neural network, which is a complete black box. And people always say, well, with search technique, you know what you're doing because you have a tree, and you know the value of your leaf nodes, and you know also how you backpropagate it, and you also know based on that backpropagation why you came to a particular decision. But even then, it's still vague. Assume we have this MCTS tree, and you say, well, I would like to go to the first move because I won like 62% of the games, whereas for the other one, it was 58%. But this in the end is simply a percentage, and that's not very explainable, I have to say. Because if you start explaining this, how you would get there, and you would simply go down the tree, you would say that at a certain moment that the values are going up and down, because you have seen these positions actually less, and the values can start going all over the place. And of course, this has been based on some random simulation. Could have been that you would also have been some smart technique, like using n-grams, where you were using epsilon greedy. And in the end, you also use a neural network to score one of the final positions. But even that is not quite understandable. And it becomes even worse as you have been selecting these states of getting there in the first place by using your UCT algorithm, that you have been biasing in some way. And moreover, you also have been using parallelization, which meant that you have been working at the tree at several places at the same time, and not in the same area, because you would like to distribute your calls in a smart way. And because of that, you also got a particular search tree, and based on that particular search tree, you also start selecting your nodes. And that is also not very understandable, how you actually came to a particular decision like this. And it becomes even worse if you're also using all kinds of online mechanisms that tune your parameters when you're doing the search. So it could be that some of your epsilon parameters or your exploration constant parameters actually change over time, actually also during the search. And moreover, at the moment, this search algorithm hasn't been designed by you anymore, but by AI itself. It becomes even more complicated to explain what actually went on. And then I'm not talking when this is also going to run on a quantum computing, because then it becomes really weird. Anyways. And this is actually the fourth adventure and also the last adventure we currently are working at. And if you're not working at it, I would also invite you, is so-called explainable search. Which means that based on the search, you try to explain a user what basically the reason was why you took a particular decision, or why you actually didn't take or went for a particular decision. And of course, you could also ask all kinds of questions like what if and how did you do it? Now, this has to be based on actually mining your search tree amongst others. So based on the shape of the tree, you could actually try to start explaining this. Maybe you also added some domain knowledge, and this context you could also use in your explanation. Or you could also use some sources from using literature to explain why you went for a particular decision, as it also complied with certain things also humans would do. And the question is, of course, how you would explain this and also take into account all different levels of users. This turns out to be actually a very complicated one, because usually with MCTS, you distribute your search in a smart way, which means that if at the moment you see a couple of promising lines, you spend a lot of energy at them, and you don't spend a lot of energy anymore at the ones that didn't look promising. But then you can't explain anymore why you actually didn't search in that direction. Well, you didn't do it because it didn't look promising, and you don't have any other explanation. Now, with one of my postdocs, we explored this domain a little bit, also seeing what kind of explanations users actually liked. We would have liked explanations with only statistics, but also maybe explanations with also some context. So with statistics, you could simply say, well, I played this move 10,000 times and won like 50% of the time. And with context, you could say, well, you saw this move in the sense that you assume you know a little bit of this game, it would create large groups, or it would capture a particular stone, etc., etc., etc. Or you could also do this in combination. And moreover, you could look at the move itself. You could also look at it in relationship with the siblings, or you could also look at the path. Now, what we figured out was basically that if you would do explanations with only statistics, the users didn't like it. At the moment, you added more information, they started to also appreciate the explanations more. Having said that, what we also figured out, if you made explanations even complex enough, then they would always think or even believe that they got a good explanation, even if the explanation was even bogus. We added also a couple of bogus explanations there, and it turns out if you make them actually complicated enough, then users also think that you're explaining something while you actually are not explaining something actually pretty well. So this is a very tricky business, and this is still an adventure, I have to say. Now, also in view of time, because also Dennis is becoming a little bit impatient. So what I'm trying to tell you is still MCTS is a very exciting research domain. So even if you have nowadays all LLMs and all these deep neural networks, you can combine with MCTS. Also researching MCTS is still cool, because still there are a lot of applications lying around in the real world where we can use MCTS. And the question is, how can we transfer MCTS there? Also, which techniques we already developed in the game AI we could actually use then. Also, to make MCTS more generic is a very challenging topic, and would also invite you to look at this. We are also going into the quantum computing area, and also MCTS can play a role there. And then in the end, explaining MCTS decision making is still a huge problem. Now, these are the 4 adventures I'm working at, and I also invite you also to dive into these adventures in the upcoming years. Anyways, thank you for listening, and if there are any questions, then please let me know. I'm sorry for my voice, because I'm now starting to lose it.
Thank you, Mark. I see Michael has his hand raised. Does that mean you have a question?
No, that was just applause, congratulating on the nice talk. Thank you, Mark. It was very good, very interesting.
I would like to follow this compliment. My name is Jaap van Erik, so I said I'm proud on him, as you may understand, because I'm produced. That means that I would say I'm proud on the PhD student who has such a fantastic thing. There was nothing what I missed. It was an abundance of facts and about future looking. But I would like to help you a little bit more, because after the ANI, the narrow intelligence, we go to the generic intelligence, the AGI. You said quite a lot of things, but then we have something in our view, a next step, and that is the step to supercomputing, superhuman computing, as you may understand. My first question, and then I come later on with the second one, but my first question is, what are the dates that you think that AGI will enter the world?
You are muted.
So yeah, I was muted. Yeah, of course, I think we still are a little bit debating what AGI actually means.
Yes.
I think that is one of the biggest problems that we currently have. I always refrain from all these predictions, because this is also being recorded.
Yeah, that's true. But let me help you.
Yeah, but let's now take it for gameplay,
Yes.
Maybe to keep it a little bit easier. I honestly believe that in, say, maybe 5 to 10 years, but let's say in 10 years, then we should have systems that could play any game at any time without any human intervention anymore.
I fully agree with you, and you are not the only one who is
really,
thinking
you give it the rules, and it should come up with something that plays the game. And of course, now you come to your other one,
Yes.
Talking about artificial general intelligence, what would be the level then? Would you be happy if this would play it at grandmaster level, strong amateur, or would you already then demand that it would play at AlphaGo level, or even could solve the game. Huh? Even. Because I think that would be your dream, that you would have a system and you would give it chess and it would then solve it for you. Huh? In such a way that you as a human designer could never have done when building such a system yourself. I think that's your dream, huh? Yeah.
You know me very well, and that is
the
correct answer.
So when would we have that?
If there are more questions, I give the floor to other people. But if there are no more questions, then I'm interested in your answer.
Yeah, because here I would like to come also here. Would you then be? We would have actually two cases, huh? The first case is you would have a system that would build such a system that could solve the game better than we as a human developer could build such a system. You could also still have systems that do that, but if we still as a human developer, we could still improve upon that. Or we could have the case that we as human developers can't improve anything and even more. Huh? So yes. You also have gradations.
Yes,
here.
I agree. Yes,
I agree.
What do you tell your PhD students?
I stick to my 10 years prediction for AGI, and for your superhuman one, I will refrain from making any prediction, because as already indicated, what do you mean also with superhuman?
I agree fully with you. And Dennis, are there more questions?
I see a hand raised from Lucas Grassauer. I don't know if he can speak or okay, yeah, he can.
Yeah, I can speak. So I've asked this question also in the Q&A, but I'm happy to state it like this. So it's a different topic, I guess. For Minimax, searching deeper is usually more fruitful, depending on the game, of course. But there is a quite clear connection that deeper is better, right? And is this also true for Monte-Carlo tree search, or is this something we could vary?
Of course, I would like to state the results that we have done so far is usually for two-player domains, but more simulations is usually better. Assuming that we don't have the pathological case. But you can, I would even say, so far what I've seen with all the research that I've done is as long if your playouts make sense, that searching deeper or searching more simulations is always better.
I agree. Let me more specify. What I meant is because we have this expansion phase in Monte-Carlo tree search. My question was regarding maybe it's not fruitful to expand so deep into the tree. Maybe it's better to keep the simulations high up in the tree.
Yeah, closer. Yeah, and I have done actual research with this with Tom Paples when we did it actually for general for the Pac-Man, which was actually real time, and there we made the conscious decision not to go that deep in the tree. So we actually limited the search depth. But this was something we did actually for a real-time search. And we never have tested this out for bigger games. But what we noticed that for when actually doing real-time search, it was actually better not to go too deep in the tree, to limit it actually a little bit. So you would also expand the other moves a little bit better. And especially if this is in real time, that's actually necessary. So to answer your questions, yes, we know of some cases where this is actually better to do. Okay. Look at our Pac-Man paper.
So is there a way to try this out with Frankensearch? Because this would
yes,
awesome.
Yes. In Frankensearch, I would have to extend the model, but that would be possible. Yeah.
Then I'm looking forward to testing it.
Yeah. And if it's not possible, I will simply put it now in the future research. Thank you very much.
You can also contact me if you want.
Yeah. Good. Thank you. Thank you very much. Love that suggestion.
Do we have any other questions? I don't see any more in the chat right now.
And then I come back to my previous question, and that is, what do you expect, I would say, for solving the game of chess?
What the outcome would be, or what the spin-off would be, Jaap?
Now, both. First of all, I'm not interested in the outcome. The outcome will be a draw. It's with all people
okay,
around
good.
it. That's true.
Yeah.
And then also we know that then we needed the proof, and then you say that could happen in a few years. But what will be the consequences of that statement?
Me, a technical one or societal one?
Let me say,
so I become also more for
yes, I'm overdoing, but let me say, could we solve it also in political sense? This could we apply and say for the Ukraine or the Gaza situation?
Yeah, of course. And that's I know what you're talking about. I know we are back to the 70s where people thought, well, if we can deal with gas, we can also deal with other strategy decision making. You know that Hans Berliner's research in the 70s was actually also funded by the Department of Defense.
Yes.
I think yes, in a political sense, I think one of the challenges that we always, or I think also the military is interested also for strategic decision making. Yeah. What would be now also for our geopolitical situation, the best way to handle things? And I do agree there with you, Jaap. I think we could model the world in such a way, also at an abstract level, that with our techniques that we have been developing, that we could say, okay, the best for Europe or the best thing for the States is to behave like this and this and this and this. And I do believe what you also indicate that our research, what we're doing, will also contribute to this. Whether this has been solving chess, whether this has been solving Go, or whether actually looking at games where there's also imperfect information, where there's also some randomness involved, this will all contribute.
Okay, thank you for your answer. Yes. You make this conference a valuable point in, I would say, on the map of the Netherlands research and also on the world research. Thank you very much.
Okay, thank you.
Okay, so since there are no further questions, I want to thank you, Dennis, again for chairing, and thanks a lot, Mark, for this very interesting keynote.